Hello, in this video we will see how an astable multivibrator will work. This is the general output waveform we get in an astable multivibrator. It will have two quasi-stable states. This is one quasi-stable state and this is another quasi-stable state. And the time for which it remains in the quasi-stable state is decided by the resistor and capacitor values used in the circuit. It doesn't have any stable states, it has two quasi-stable states. This is the circuit diagram of a stable multivibrator. Coming to the construction, it will have two transistors Q1 and Q2, and the collector terminals are connected with resistors RC1 and RC2. And the base terminals of Q1 is connected to the collector of Q2 through the capacitor C2. The base of Q2 is connected to the collector of Q1 through the capacitor C1. And in general, this RC1 value will be less than RP2 and this RC2 value will be less than RP1, so that the capacitors charge. By connecting the collector terminals to the base of other transistor, this process is called cross coupling. The working of the circuit can also be referred in the link given in the previous slide. Initially, we have two transistors, so transistor can act as on switch or off switch. Whenever the base terminal of the transistor is less than 0.7 volts, it will be acting in cutoff region, and in that case it will act as open circuit or off switch, and its collector point VCE will be at VCC potential. And whenever the transistor base terminal is greater than 0.7 volts, any transistor, the base terminal is greater than 0.7 volts, then that particular transistor will come to saturation level. In saturation, it will act as on switch and it will be short circuited, and its VCE voltage will be at 0 volts. Initially, when power supply is not given, both the transistors will be in non-conducting state. But when the power supply is given, both the transistors will try to conduct. When both the transistors will try to conduct, the capacitors C1 and C2 will charge in the direction shown here. And due to the transistors are not exactly identical, due to mismatch in the transistors, one transistor will conduct, another transistor will not conduct on and off. They will complementarily act as on and off switch due to mismatch in the transistors. So for convenience, let us assume Q1 transistor is in on state and Q2 transistor is in off state in the beginning. Based on this, we have assumed Q1 transistor on state, so it acts as short circuit. In saturation region it is operating. We assumed Q2 transistor in off state, so it will be open circuited, it is acting in cutoff region. And because of Q1 transistor on state, the capacitor C1 will be conducting through this direction, and its potential will be VCC minus VBE. And as one side the capacitor is connected to ground level because Q1 transistor is in on state, other side this negative potential is supplied to the base of Q2 transistor. As negative potential is given, this Q2 transistor will come to off state. So when Q1 is on, Q2 will be in off state. And at this situation, this Q1 transistor on state, its collector voltage will be 0, and Q2 transistor is in off state, its collector voltage will be VCC. We take outputs at both the collector terminals of the transistors, and hence these two 0 volts and VCC are the output voltages we are getting at the collector points of two transistors. These are the outputs of a stable multivibrator when Q1 is on and Q2 is off. This is our present situation. Q1 transistor in on state, Q2 transistor in off state, and As Q1 is on, both the capacitors will try to charge in this direction shown here, and the C1 will charge through RP2 and Q1 transistor, C2 will charge through RC2 and Q1 transistor. This C2, the voltage level will be VCC minus VBE, and C1, because Q1 is in on state, C1 will be charging to the voltage level VCC. It will try to charge to the voltage level VCC. As Q1 transistor is on state, it will act as short circuit, and because of this short circuit, Q1 transistor on state, because initially we considered here Q1 transistor on state, it will be in short circuit condition. So capacitor one end will be grounded through Q1. Other end is connected to the base of Q2, and this is at ground level. It will try to charge to VCC. On the way, when the voltage is equal to VBE of the second transistor, 0.7 volts, when it becomes 0.7 volts, as this is connected to the base of Q2 transistor, it will try to make the Q2 transistor on state, and hence Q2 transistor will come to on state saturation level, and the C2 capacitor will be charging. Its potential will be VCC minus VBE, and this point is connected to Q1 transistor. Other end it is connected to ground because Q2 has come to on state. This negative voltage is supplied to Q1 transistor, so Q1 will come to cutoff situation, off switch, open circuit. Now what has happened? Beginning we started with Q1 on and Q2 off, but finally it came as Q1 off state and Q2 on state. This is our present situation based on the operation. We will be getting the voltage at the off transistor VCC. So earlier it is 0, now it is switching on to VCC. On the other side, earlier it was VCC, now it is switching to 0 level. Earlier it is VCC, now it is switching to 0 level because it has come to on state. It is at VCC when transistor is in off state. Now transistor is in on state, Q2 transistor is in on state, and hence it has come to 0 level. These are the outputs of stable multivibrator collected at the collector terminals of transistors. Now our present situation is Q1 transistor off and Q2 transistor on. We will start with this Q1 transistor off and Q2 transistor on. This is our present situation, Q2 transistor on. So whichever transistor is on, both the capacitors will try to charge in this direction. Now C1 capacitor will charge through the resistor RC1 and through the Q2 transistor. C2 capacitor will charge through the resistor RP1 and through the Q2 transistor. Now the voltage level at C1 will be VCC minus VBE, and the C2 capacitor, as Q2 is on state, it is short circuited. The one point is connected to ground, and now C2 will try to charge to VCC, and on the way when it crosses 0.7 volts, it will be switching on Q1 transistor. C2 transistor, one end is connected to ground and it is trying to charge to VCC level, but when on the way it gets a charge of 0.7, it will switch on this Q1 transistor, and here the voltage is VCC minus VBE. The negative end is connected to the base of Q2 transistor. Q1 has come to on, other end it is connected to ground level, so this side negative potential it is given to the base of Q2 transistor. Because of that, Q2 transistor will come to off state. Now Q1 transistor is on and Q2 transistor is in off state. We started off with Q1 transistor off and Q2 transistor on. At the end, we are coming up with Q1 transistor on state and Q2 transistor off state. Whichever transistor in off state, the voltage is VCC. Whichever transistor is in on state, the voltage is 0 volts. Hence, it is switching on from VCC to 0 because the transistor is in on state, 0 voltage is the output now. and here off state transistor it will give 0 to VCC switchover, and these are the outputs we are collecting now at the collector points of the two transistors. These are the outputs of unstable multivibrator. This is the circuit, and complementary outputs are obtained at the two ends of collector points of the transistors. So when first transistor giving on state higher voltage, second transistor will give 0 level. When first transistor giving 0 level, second transistor will give higher voltage, and the time for which it is remaining in each of these quasi-stable states will be decided by the values of RB2 C1 and RB1 C2. These two resistors and capacitor pairs will decide the time for which it is remaining in the quasi-stable states. Now we will try to derive an expression for the time it remains in one quasi-stable state. Now Q1 transistor is in on state, and C1 capacitor, it will have a initial value of VCC minus VBE, and it will try to, because it is on, it is connected to ground, now it will try to charge to VCC level. Final value is VCC level, initial value is minus of VCC minus VBE. And this is the equation for capacitor voltage. Capacitor voltage equal to V final plus V initial minus V final into e power minus T by RC. This is initial value of the capacitor minus of VCC minus VBE, and then final value it is getting charged, trying to charge to VCC level because Q1 transistor is in on state. Q1 transistor on state, it will give a value 0 volt, and this is the one of the quasi-stable state. We are trying to calculate time for which it remains at the 0 level. Now we will try to calculate after T1 this capacitor voltage will reach VBE, which is 0.7 volts, to switch on Q2 transistor, and at T1 the capacitor voltage will reach VBE. Putting all these three conditions in the first equation, we will get VBE equal to VCC final value plus initial value is minus of VCC minus VBE minus final value VCC, and this T is capital T1, RC is nothing but this RB2 and C1. These two will decide the time for which it remains at the 0 level. And when we bring the exponential to one side, all the other parameters to other side, this is the equation we are going to get. We know that supply voltage is always very much greater than the cut-in voltage of the transistor, so VBE is negligible compared to VCC. When we neglect, we will get a value like this, 1 by 2 VCC minus VCC will get cancelled, and when we simplify this, when we take T1 as subject, minus RB2 C1 ln of 1 by 2, and the value becomes 0.693 RB2 C1. Similarly, when Q2 is in on state, Q1 is in off state, it will give VCC voltage, and the time for which it remains in VCC is T2. Similarly, the resistors RB1 and C2 will help in giving this VCC level at Q1 and at the same point 0 level at Q2. So the same equation can be replaced for T2 provided the other set RB1 and C2 will decide the value of T2. Now the total time period in the output obtained at any collector point will be T1 plus T2, and it is 0.693 RB2 C1 RB1 C2. When the two resistors are of equal value, two capacitors are of equal value, we will get 1.386 RC. 0.693 into 2 times RC, which becomes 1.386 RC. And frequency is inverse of time, we will be getting 0.72 by RC. This is the ideal case of output obtained at the collector points of astable. Practically we will not be getting like this small the charging of the capacitor will give this curve shape for the output. In order to get ideal curve, ideal waveform like this, we have to adjust the values of resistors and capacitors so that we will be getting a sharp ideal type of waveform, two quasi-stable states. If both resistors and capacitors they are of equal values, then we will get a symmetrical square wave like this. If the resistor values are different, both resistors are different values, both capacitors are different values, then we will be getting unsymmetrical square wave. Conclusion: this is a stable multivibrator. The outputs obtained are complementary at the collector points of two transistors. Other name is free running multivibrator. Time period we calculated 0.693 R1C1 R2C2, and when transistor is set to be on state, it is in saturation region, short circuited. When transistor is set to be in off state, it is cut off region, open circuited. When Q2 transistor is in off, then C1 capacitor will charge to VCC, C2 capacitor will charge to VCC minus VB. Similarly, when Q1 transistor is in off state, C2 capacitor will charge to VCC and C1 capacitor will charge to VCC minus VB. And the two transistors, they will be in complementary action. One transistor on, other transistor remains off. And these are a few questions based on a stable multivibrator. A square wave oscillator is given by a stable multivibrator. It is having no stable states, both are quasi-stable states, and it will generate a square waveform of its own, a stable multivibrator. All the multivibrators will come under relaxation oscillators category, and no stable states are present in a stable multivibrator. We have one gate question in 2009. A stable multivibrator can be used for generating square wave. Bistable multivibrator can be used for storing binary information. Which of these two statements are correct or wrong, any contradictory, or based on one on the other? Bistable, other name is flip-flop. Flip-flop is 1-bit storage element, so it can be used as storing binary information. Astable, as we discussed, it is used for generating square wave. So both the statements are correct. Option C is the correct answer. Thank you.